Before I start lecture number 9, as we did before, let's review what we learned in the last lecture. Okay. First, I emphasize that the resultant force induces motion, that is force law, or alternative expression of force law is resultant force may induce change of momentum. And secondly, we learn about principle of impulse and momentum. If I write that in vector form, linear momentum at state 1 is going to be changed by impulse which I apply to the mass system, impulse 1, linear momentum 1, will induce the momentum change at state 2. Thus, we call principle of impulse and momentum. And the third we learn is principle of work done and change of kinetic energy. Mathematical expression would say if I apply force from state 1, 2, that induce work done, that will make change of kinetic energy. If the force is conservative, for example, if there is no friction force, then energy will be conserved from state 1 and state 2. Note that this expression is a scalar energy equation, and the other equation is in vector form. Okay, so let me put some symbol on this method. Newton's second law, star, linear momentum, maybe I put moon, which is smiling, and let me denote that this is star because it is related with energy. Not the star, I'm sorry, sun. Okay. So we have to select star, moon, and sun for each problem of interest. In other words, the problem you want to solve. Okay. Now, I have two mass which has the same shape as well as the volume, and if I throw this to you, okay, you observe that there is some rotation as well as translation. If I throw that, that has different mass, okay, but look like same rotation. It's rather interesting. So these principles also can be applied to each mass, right? And let's start to study again these principles to the system of particles, okay? To understand what's going to happen on system of particle, let's just see two particle case, as I demonstrated before. Okay. Okay, we have a two particle. And because to apply these three laws, we need coordinate. Let's call this is x, y, z, and the origin of coordinate is 0. Okay? I intend to look at the motion of these two particles from here, as well as the coordinate over here. So I'm going to argue that the motion which I observed from here is the combination of the motion that I observed from here. Specifically speaking, I want to see the motion of the system of particles as if all the masses are concentrated on mass center. That's what I'm seeing, the motion over this point. Okay, and also I want to see the motion separately. In other words, I want to see the motion that is observed at the center of rotation. So I can argue that the whole motion would be the motion I observe observe spelling. Or I would say, observe the motion over here. That is, observe the motion with respect to O, x, y, z is equal to motion of center of mass plus the motion observed with respect to the coordinate that is attached to the center of mass, which I call x prime, y prime, and z prime. Okay, this is the central concept that allow you to understand correctly the rigid body dynamics. Okay? This is central concept. So I will make yellow block, the red block over here. Okay. Now, suppose I have a center of mass over here, and I denote that is G. Okay. Then if there is a force applied to that particle, which is F1, and I may have a force F2 over there, that is like I am applying the force over here. Right? And I want to see how these two particles is moving due to that applied external force. The force inside is internal force. As we saw before, the effect of internal force to the motion of this system of particle is 0. Okay? So let me use the Newton's second law, because there is only force and the motion. So I select Newton's second law. Okay? And express the Newton's second law graphically to avoid any possible mistake. So that says here is two particles. and there is a center of mass. And I am measuring this acceleration with respect to the coordinate over here. Sorry. And I may denote, okay, let's remove with the acceleration of A1, and this may move the acceleration A2. Okay, that graphical expression is correct, right? Is it correct? If somebody asks, no, it is not correct, we have to consider the internal force F12, F21, because Newton's second law star applied to each particle. Which one is correct? Answer. Do we have to consider this internal force to apply Newton's second law? Or the argument to say that F21 and F12 is equal and opposite, therefore those effects are nothing? Which argument is correct? Look at this equation. This equation says all the force applied to the particle or all particle will induce the motion of a particle, the particle. So strictly speaking, we have to consider these two forces to correctly use the Newton's second law. Right? At least by considering these two internal forces to apply Newton's second law, certainly avoid any mistake. If it is not really affecting the motion, then the result, Newton's second law, will teach us those internal forces. It's not affecting the motion, MA1 vector and MA2 vector, and you are not supposed to make any dangerous assumption. The law will show you which one is correct. Okay? That is a very important message. You are not supposed to make any dangerous, unreasonable assumption that you are not sure. Okay? Then you just say there is some force acting on the particle of interest that you are going to apply. Okay. Now, so, very hot. Next, we learn that from this picture we can say all the resultant force will be M1A1, or the resultant force acting on the mass 2 has to be M2A2. And also in the last lecture we found that because we are handling all the vectors, if I take a moment with respect to this point and denote this is position vector R1 and position vector R2, that indicate where the mass 1 and the mass 2 is, R1 and R2. And I take a moment, which is simply a summation of Ri vector cross product Fi vector. And we argue that that is equal to angular momentum h0, change of angular momentum with respect to time. And notation is very simple. Okay. This is what you understand mostly. This is what? So let's look at what is angular momentum is. What is the physical meaning of angular momentum with respect to coordinate O, X, Y, Z. And in fact, I'd like to relate this expression with the angular momentum that I could observe the coordinate which I may use G, X prime, Y prime, Z prime. So that I call HG vector. This is also vector, I am emphasizing. Therefore, this HG vector can be expressed with respect to O, X, Y, Z, or this HG vector can be expressed with respect to G, X prime, Y prime, Z prime. Yeah? Yeah. Because vector has to be measured with respect to certain coordinate. Right? This is pretty much related with relative coordinate we already learned. For example, the position vector RA is equal to position vector RB plus position vector R that observed with respect to B. And we also know that the velocity of A is equal to velocity of B plus relative velocity of A with respect to B. Acceleration of A is equal to the sum of acceleration of point P, relative acceleration of A with respect to B. Okay, those concepts are on the same track, actually same concept. Okay. Unfortunately, the textbook just described those concepts is rather, in terms of my understanding, complicated way. And my purpose of this lecture is to clarify those relations. Okay?